Welcome to day 6 of exponential and log functions. Today we're going to talk about recursive notation as well as some more application problems and general equations that we use. So recursive notation, this means that you have a sequence of numbers and there's some repetitive nature of how you go from the first term to the next to the next. So for instance, we have 5, 8, 11, 14. What is the pattern of how we advance in this series? And since they're getting bigger, we're either adding or multiplying by something. And in this case, it looks like we add 3 to each number to get to the next one. So if we want to write that as a series, or with recursive notation, we first have to designate what is the original term. In this case, the original term is 5. So A says it's part of the series. 0 means the original value. So the original value in this series is 5. And then we also write if we want any element of this series. So the nth term, so that's not a base, it just is an index number. So if I wanted the 10th term in the series, n would be a 10. But the way I find the nth term is I take the previous term, so if this is 10, I would use a 9 here, and to be generic, we just say n minus 1. I take the previous element, and in this series, I add 3 to it to get to the next term. So this is my recursive notation right here. Let's look at a couple of these. So here we start with 216, so that's my a sub 0 value, and then I'm getting smaller and smaller. And the way I get smaller, it looks like, is I divide by 6. So the next element in this series would be 1/6. And my recursive formula, the way I find each term, is to find the nth term, I take the n minus 1 term, so the one that comes right before the one I want, and I then divide that whole thing by 6. Second line here, we're getting smaller and we're going down by an even amount. We're going down by 4 each time. So the fourth term here is 67 because I take the third term and subtract 4. So my recursive notation is that if I want the nth term, I take the n minus 1 term and subtract 3 from whatever this term was. That's all the recursive formula does. In this case, we are adding 2.5. So my recursive formula is a sub n equals a sub n minus 1 plus 2.5. That's all recursive notation is giving you a formula of how to find each term based on what came right before it. Okay, but the meat of today is these handy exponential equations. We can have exponential decay or exponential growth. Let me just cover this up so we can look here. The only difference in these two equations is if it's decaying or getting smaller, we will subtract the percentage. If it's growing, we add it, so it's getting bigger. And in these formulas, y is always what happens in the future. A is the amount you start with. R is your percentage of change. And T is your time. And the problem will tell you what unit of time you're using. So for instance, if let's say our population is 500, and let's say we're growing at a 4% growth rate. And we want to see what happens in 15 years. I'm telling you we're growing, so that means I'm going to use the growth model. So to calculate this, A is what I start with. So I have 500 people, and I'm growing. So 1 plus, I take my percentage as a decimal. So that would be 0.04 raised to the power of whatever time you want. In this case, it's 15. I now would just take that and plug it in your calculator. So 500 times 1.04, so I've just added those together, raised to the power of 15. And I get that my population is going to be 900 people. Because since this is people, we're going to round to the nearest whole number. Okay, so if it's something, a unit, you just want to round that off. If it's just a number, a mathematical expression, we want to keep 3 decimal places. So that's an example of exponential growth. We also have compounding interest, which is the much more interesting one. This is ones that deal with money. And if you notice, this is very much like our exponential growth equation, but we added in the ends right here. And the ends are important because when you're compounding interest, you need to know how often it is compounded. So if you're compounding monthly, n will equal the number of times in a year that would happen. So if it's monthly, you compound your interest 12 times during the year. If it was, let's say, quarterly, then n is going to equal 4. And notice that n falls in the equation twice. So let's do another example here. Let's say that we have $5,000. Why not? And we are going to earn a 7.5% interest. And let's say it's going to be compounded, let's do monthly. The way we set up this equation, so that A is going to be what's in the future here. A is going to equal your principal, or what you start with. In this case, it's 5,000, multiplied by 1 plus, because again, we're growing, 0.075 divided by, since this is monthly, n is going to be not 4, but 12. And this is going to be raised to the power of 12 times t. So that's the generic equation. If I told you to calculate after 3 years, then we would enter 1 plus 0.075 divided by 12 raised to the power of 12 times 3, because that's the number of years. And I will type this in the calculator exactly how I've written it here. So we would clear 5,000, 1 plus 0.075 divided by 12, all of that raised to the power of 12 times 3. And I know you know what that is, but it's a good habit to get into entering everything. So we would have $6,257, and we want to keep 2 decimals because it's money, so 23 cents. And that's how that would work. So again, the key thing with compounding interest is you need to know how often it's compounded. Another one with money is compounding continuous. And this formula, notice there's no n in it. So this assumes that you're compounding every second. It's constantly happening. So using our same scenario here, except it's not monthly, we're going to have, in the future, we will have our principal, which was 5,000, times e. And again, remember, that's just a constant. It's in the calculator already. Raised to the power of 0.075 multiplied by 3, because we want it after 3 years. And do you think if you compound continuously, it's going to be bigger or smaller? It should be bigger. So let's take a look here and see what happens. So I plug this in the calculator, 5,000 e, and the way I'm going to get that is second ln, because notice it gives you the e and the caret, and the parentheses of 0.075 times 3. So that's my interest rate as a decimal times the number of years, and I get $6,261.61, which if you look here, that is more than we got when we were compounding monthly. So generally, the way to think of this is that more frequently you compound, the more you earn. So large compounding is good. Okay, a couple of other formulas we have on here is a half-life formula. And what this is if you have some sort of isotope that's decaying over time. Our rate right here is 1/2. And that comes from finding out how much of that is left after its half-life. So the amount of the material you start with multiplied by 1/2 raised to the power of t, and t is in the time, whatever the units are that they give you, divided by the half-life. So for instance, if I told you chromium has a half-life of 23 hours, and I have, let's say, 100 grams, I want to know how much would I have after, let's say, 60 hours. How much it would be left. So I would plug this in as my ending mass is going to equal my starting mass, which was 100, times 1/2, raised to the power of t, so 60, divided by the half-life, which was 23. And once again, I'm just plugging this straight in the calculator. So 100 times 1 divided by 2, raised to the power of 60 divided by 23. So I would have 16.39 grams of material left after 60 hours. The last formula on this sheet is a formula that we derived from Newton's law of cooling. And this is a formula that's used to calculate when a person died, basically. So we will have T representing the body's temperature. So if the coroner, for instance, or the medical examiner measures the temperature of the body, minus the temperature of the room around the body, or the air, and then the normal temperature of the body, which is 98.6 minus R, calculate that, take the natural log of it, and multiply by -10. That gives you the time since the person died. So for instance, let's just make up something here. If we say the body is 80 degrees Fahrenheit, and the room, I don't know, let's say it measures 74 degrees Fahrenheit. We want to calculate when the body died. So let's say it's 10 p.m. right now. So we want to see how long ago did this person die. We're going to plug in, time is going to equal -10 ln, the temperature of the body, which is 80, minus the room, which is 74, divided by 98.6 minus 74. And of course we can't just cancel those 74s. We have to calculate. So -10 ln, 80 minus 74 is 6, 98.6 minus 74 gives me 24.6. And I'm not even going to calculate this at this point. I'm not going to divide it. I'm just going to plug it straight in the calculator. So -10 times the, not right, -10 ln of 6 divided by 24.6, and that gives me 14.11. So T equals 14.11 hours. That means 14 hours and a certain number of minutes ago, this person died. So if I wanted the minutes, it's 14 hours and then 0.11 times 60. 0.11 times 6 is, so 6.6, we'll round that up to 7 minutes. So 14 hours and 7 minutes ago, this person or this body died. 14 hours before 10 p.m. would be, let's see, 10 a.m., 8 a.m., and 7 minutes more, so that would be at 7:53 a.m. And if you watch crime shows, you know they never give it to you that exactly. But using this formula, that's how we would come up with the time. Okay, so we have a lot of problems in this packet for you. So let's just do a couple of them so you get the feeling of how to work this. Here we go. Let's try number 9. So the current population is 7.414 billion in 2016. In 1996, it was 5.68 billion. If the population continues to grow at the same rate, so that means we've got a constant growth rate, what year will the population double as compared to 1996? Okay, so the first thing is we don't know the growth rate, but we do know the difference in the growth, and then we want to figure out how many years does it take to double. So we've got to do 2 problems, do this in 2 steps. First part is we take our starting population, this is going to be a growth, exponential growth. So my ending population is 7.414. My starting population was 5.68 billion. and 1 plus r, 'cause I don't know what the growth rate is, and then raised to the t. I do know what t is, though, and I get that from 1996 to 2016. That's 20 years. So to solve this problem, I'm going to divide both sides by 5.68. So 5.6, oops, let's clear that. 7.414 divided by 5.68, and I get 1.3053. We always want to keep as many decimal places as possible. So that equals 1 plus r to the 20th. Now, since my variable is in the base, this won't help me to rewrite it as a log. So the way to get this by itself is I need to raise it to the reciprocal power. So if this was raised to the 20th power, I'm now going to raise all of that to the 1/20th power. And same thing with the other side. Because 20 times 1/20th cancels and gives me 1, or multiplies and gives me 1. So the right side is just going to be 1 plus r. The left side, I'm going to take that value, and notice that in my calculator I've left this, I didn't round it. I'm going to raise that to the 1 divided by 20 power. So I get 1.013. I now need to subtract the 1. So 0.013 equals r. So that's my growth rate. And this is already as a decimal. If I wanted it as a percent, I move the decimal over 2. So 1.3 is the percentage that we are growing. Now I need to come back to actually answer the question here. In what year will the population double compared to 1996? So 5.68 doubled, so times 2, it's 11.36. So what year will the population be 11.36 billion? If I start with 5.68, raised to the, or multiply by 1 plus 0.013, raised to the t power. That's a t up there. Okay, so first thing we need to do is divide both sides by 5.68. And we know, what value does that have to be? That has to be 2 because we want it to double. And notice I've combined the 1 and the 0.013. Now if my variable is in the exponent, the way I solve this is rewrite it as a log. So this is log base 1.013 of 2 is equal to t. Now we know how to solve this type of equation. We do our change of base, log of 2 divided by the log of the base, 1.013. And when I plug that in my calculator, we get log of 2 divided by log of 1.013. Need those parentheses. We get t is equal to 53.7. Remember, these are years. So in 53.7 years, our population will have doubled. But I want the actual year. So I go back to my starting year, 1996, and I'm going to add this. I'm going to round this to 54. So our population will double in the year 2050. That is the year that the population doubles relative to 1996. Okay, good luck. Always write down everything you know, as well as trying to figure out what is it you don't know, what variable that is, and how do you combine those things. Good luck.